In section 11.4, we're going to talk about geometric probability. To start, let's discuss some vocabulary. So the probability of an event is the measure of the likelihood that the event will occur. It is a number between 0 and 1 inclusive, and what that means by inclusive is that it can be 0 and it can be 1. So 0 and 1 are included in every number in between 0 and 1. It can be expressed as a fraction, decimal, or percent. We'll probably see them the most as fractions and as percents. The probability of event A is written as P of A, and the way you would read that is the probability of event A happening. So if we're talking about the probability of flipping a coin and getting heads, it'd be the probability of heads, and I would be written like this: P of heads, so the probability of getting a heads as you are flipping a coin. The probability, again, can be any number between 0 and 1. If it's equal to 0, that means that the probability is impossible, that the event is not going to happen at all. If the probability is 1, as in like 100%, that means that it's absolutely certain that that event will happen. If you're halfway at 0.5, you have equally likely to occur or not to occur, so you have like a 50-50 chance. If it's at 0.25, it's going to be unlikely, so like a 1 in 4, a 25% chance. If you have or around a 0.75 or a 75% chance, 3 out of 4, then it's pretty likely that it's going to happen. It's not absolutely certain that it will happen, but it is pretty likely. And what we're going to be doing in this section, once again, is applying this probability to geometric situations. The first way we're going to do that is by combining the idea behind probability and the idea of length. Let segment AB be a segment that contains segment CD. So if you look at this diagram, you have segment AB and CD is inside of segment AB. If point K on AB is chosen at random, so I'm picking any point on segment AB, then the probability, so the likelihood that it is on CD, is the ratio, which means fraction, of the length of CD to the length of AB. So the probability that K is on CD is the length of CD, so the length of segment CD, over the length of AB, so the length of segment AB. So if AB was 10 units long and CD is 7 units long, I would have the probability that K is on segment CD would be 7 out of 10. So out of those 10 units between A and B, I have 7 units within CD that I could put K for it to be on CD. So the likelihood that K is on CD is a 7 out of 10 chance, so a 70% chance. So let's look at an example. Find the probability that a point chosen at random on AE, so we're going from A to E, is on segment CD. So the first thing I want you to do is find the length or the measure of AE, and that's just done by counting. So there are, starting at A, 1, 2, 3, 4, 5, 6, 7, 8 units between A and E. So when we do these, we know that everything's going to be out of 8 because it's the length of the smaller segment over the length of the big segment. So if the big segment has a measure of 8, then all of these would have an 8 in the denominator. So then we just have to find the lengths of the smaller segments. So from C to D, that would be 1, 2, 3 units. So I'd have a 3 in 8 chance that a point chosen at random would fall on CD if CD lies within AE. For AB, that is 1, 2 units long, so I have a 2 in 8 chance, which is a 1/4, a 1 in 4 chance that a point chosen at random on segment AE also lies on segment AB. And from B to E, so we start here, 1, 2, 3, 4, 5, 6. So I have a 6 in 8 chance, which in lowest terms is 3 out of 4. So I have a 3 in 4 chance in order to get a point on BE. Of course, I could change all of these into decimals. So to change a fraction into a decimal, you just take 3 divided by 8 in a calculator. You get that decimal, which 3 divided by 8 is equal to 0.375, and then to change that to a percent, I just move the decimal point 2 places to the right, which is equivalent to multiplying by 100, so I would have 37.5%. So just pay attention to the instructions on whether to leave your answer as a fraction, a decimal, or to change it into a percent. Example number 2, a train leaves the station every 30 minutes. Your trip to the office takes 18 minutes. One morning you arrive at the station at 8:15. You need to be at work by 8:45. What is the probability that you will be there by 8:45? So let's think about this. If it leaves the station every 30 minutes, when you got there at 8:15, the train could have just left, so the maximum amount of time that you could wait would be 30 minutes. So once again, if the train had just left when you arrived at the train station at 8:15, the maximum amount of time you could wait for another train is 30 minutes. But you need to be to work at 8:45. So if you wait another 30 minutes, that means the next train would show up at 8:45, but that's the time that you need to be arriving at work, and it takes 18 minutes to get to work once you're on the train. So what we need to figure out is what is the absolute latest you could leave the train station to travel 18 minutes to get to work by 8:45. So what I'm going to do is take the 8:45 minus the 18 minutes to get the time in which you need to be on the train by in order to get there on time. So again, I would take 8:45 or just 45 and subtract the 18 minutes, and I would get 27. So that means that at 8:27 or any time before that, you should be on the train in order to be at work on time. So the most I could wait would be from 8:15 when I first get there to 8:27 and still arrive on time. So I could wait 12 minutes more and still get there on time. But the maximum amount of time that I could wait, and regardless of whether I'd be there on time or not, would be 30 minutes. So I have a 12 and 30 chance that I will get to work on time. So in lowest terms, that would be 2/5, which means if I arrive there at 8:15, I have a 40% chance of getting to work on time. Next, let's combine the idea behind probability with that of area. So it states, let J be a region that contains region M. So we have the blue area, J, that has the red M area inside of it. If a point K in J is chosen at random, then the probability that it is in region M is the ratio, so the fraction, of the area of M to the area of J. So the probability that K is in region M would be equal to the area of M divided by the area of J. So what's really just saying is if I pick some point randomly in J, if it was also in M, I would find it by doing the area of M divided by the area of J, just like I did for length. Let's look at example number 3. A dart game uses a target with concentric circles. Concentric means that we have circles inside of circles and they are sharing the same center, with radii 5, 8, and 12. So let's label that in the diagram. So once again, the smallest circle has a radius of 5, the bigger circle has a radius of 8, and the biggest circle has a radius of 12. A dart is thrown toward the target. If the dart is equally likely to land on any point of the target, what is the probability that it will earn 20 points? So really what we're trying to figure out is what is the probability that it lands in the smaller circle versus anywhere out here within the two bigger circles. So what we want to do, according to the last slide, is we want to take the area of the smallest circle divided by the area of the biggest circle. So we'll start by finding both of those areas. Remember, the area of a circle is pi r squared. So if I'm finding the area of the smallest circle has a radius of 5. So pi times 5 squared. 5 squared is 25, so I would have 25 pi as the area of the smallest circle. For the area of the biggest circle, it has a radius of 12. So pi times 12 squared is 144, so I'd have 144 pi. So when I go to find the probability of earning the 20 points, I would take the area of the smaller circle, 25 pi, over the area of the biggest circle, which is 144 pi. The pi's would cancel. Pi divided by pi is 1. So then I would just be left with 25 over 144. There is no number that goes into 25 that also goes into 144, so that would be my fraction. As a percent, that would be found by dividing 25 by 144 and then moving the decimal point 2 places to the right, which is the same thing as multiplying by 100. When you do that, you get about 17.4%. So you have a 17.4% chance of hitting the 20-point circle versus anywhere in the entire circle. Our last example, number 4, a community sets aside a sanctuary area for birds. If a bird is equally likely to be anywhere in the sanctuary, estimate the probability that it will be in the wooded area. So remember, to do probability and area, you take the targeted area, which in this case is the wooded area, divided by the total area of the entire sanctuary. So we need to figure out the area of the open field and the area of the wooded area so that we can divide the wooded area divided by the total area of the woods. Since they gave us the picture of the sanctuary on a grid, we can just count boxes to find the area. So let's do the open field first. So let's first count how many full boxes we have. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then let's figure out what all of the partial boxes would be approximately equal to. So when I look at this, I would say that this little square and these little pieces up there account for one more. So that would be 12. And then if I combine these pieces here, there's another full one. So there is 13 within there. And then I would say that this one's almost a full one, so there's 14, and then we have a half, so why don't we just call that 15 when we put everything together. So the open field would be about 15 square feet or whatever they are measuring this in. For the wooded area, let's start counting boxes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And then if I put these two boxes together, there's 23 and 24. So the wooded area would be 24 square feet, or again, whatever they are measuring this area in. So the total area would be that combined. So we would have 38 square feet or whatever for the total area. So when I go to do the probability of the bird being in the woods, 38 would be on the bottom. And then our targeted area was the woods, which had an area of 23. So the probability of the bird being inside the wooded area of the total sanctuary for the birds would be 23 out of 38. So if I change that to percent, I would take 23 divided by 38 and then move the decimal point 2 places to the right to get about 60.5%. So you have about a 60% chance of the bird being in the wooded area versus anywhere in the entire area of the bird sanctuary. That's it for this section. Make sure you jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.